Welcome to the course on power quality. We discussed today power factor corrected bridgeless buck boost converters of isolated configurations. Why we require the isolation? In these converters, the galvanic isolation is a principle of isolating functional sections of electrical system to prevent current flow. No metallic conduction path is permitted. So, energy is exchanged via capacitance or inductance or electromagnetic wave or optical wave or acoustic wave or mechanical means like. So, where it is required, why we required it, in what application we require. So, it is used in critical power supply where fault tolerance is of utmost importance. An isolated converter is used in power supply for medical equipment with a high level of protection and safety issues for various agencies and customer demand, and output quality can be conferred to be either positive or negative depending upon the requirement because of the isolation like. So, the major 4 applications are like medical equipment of isolated DC-DC converter, PFC converters, high voltage circuits, power metering systems and typically IGBT controllers like. So, the medical equipment we use in X-ray generator, artificial respiratory system, mass spectroscopy, ECG, EEG, EMG machines and MRI machines, ultrasound and CT scanners. There we need the kind of power supply like. In a high voltage circuits, we need for high voltage and high power applications, high power drive application, high power industrial tool and telecommunication system. So, these are some of the applications where we use this typically of power factor corrected isolated DC-DC converter. Another set of applications is power metering system. You want remote reading of the meters and high voltage isolation requirement on of the order of around typically 4 kV alternating AC circuits and compact enough to size to fit easily in most of the electrical meter, as you can see typically the kind of photographs. And another set is IGBT controllers. So, this is typically from the photograph you can see that this is high frequency and in particular the very fast slew rate or rate of change of voltage over the time dV by dt puts enormous strain on the DC-DC transformer isolation, which can lead to time to isolation failure. So, therefore, for IGBT circuit the higher the isolation is considered the better one. So, an emerging solution which is coming up is the kind of welding machines, high frequency welding machine. And high current requirement is of 80 ampere to even 12 kiloampere, and high frequency transformer are used with reduced size and reduced weight and reduced losses, and switch mode power supply is using a high frequency is used in these applications. So, coming to like a typically analysis, design, simulation and performance of power factor corrected isolated bridgeless flyback converter. This is a typical circuit that you can have after the diode rectifier. We have a EMI filter, you have a typically the diode rectifier, and then we have of course your power factor corrected flyback converter, which can operate of course in your discontinuous conduction mode. For discontinuous conduction mode, we have to design this you can call it flyback inductor or transformer in its magnetizing inductance in discontinuous current mode, or if you want like a typically operation in CCM, then we design accordingly for continuous current in case of your typically in this your flyback inductor. So, the isolated flyback converter with the power factor correction, the flyback converter is a buck boost converter with the inductor split to form a transformer, so that the voltage ratio are multiplied with the additional advantage of galvanic isolation and very less number of components, and widely used in power supply with high frequency isolation, and it is used for you can call it for very wide power, very low power from even a fraction watt to the hundreds of watt like. Another of course is typically you can call it we need virtually multiple output in many applications, not only the one output, you may require multiple output also in many applications, like the kind of another maybe like a typically like your light electric vehicle chargers. So, plenty of vehicles applications are there, we need this isolated power factor corrected converter. Of course, the bridgeless version of this is shown here. The bridgeless version in the sense we have eliminated the diode bridge, and of course, on the cost of that we have to now use the almost like a couple of MOSFET, not single MOSFET. Of course, the secondary circuit, I mean, you can call it remain the same, it may be multiple output also, but a primary side. So, you of course, you are able to eliminate the diode bridge, which certainly enhances the efficiency up to some extent. So, here of course, we have a typically again the power factor correction with the you can call it with the reduced TAT as well as no reactive power burden on the supply session. So, that is of course, there have been many versions. This is the first bridgeless isolated flyback converter, and this is the second, you can call it the circuit configuration, which can be for little higher power, and because you have a two different kind of, you can call it one for positive half cycle, another for negative half cycle. So, you have a virtually two separate transformer, and typically operating with the given a many some application you can even derive the midpoint also from here, but otherwise I mean you can have a like a push pull kind of configuration rectification with the even you can call it kind of full wave rectification, which again the reduces the losses in the output also like. So, we are able to reduce the losses. Of course, we are eliminating the bridge partially as well as at the input side, I mean for rectification, as well as we are taking a minimum component in series on the secondary side at only at one diode, while you conduct the losses are also minimum in the output side also. And of course, you can design it either in CCM or DCM as far as the your number of sensors and components are required for the control like or control approach accordingly like. So, that also depends like I mean we have already discussed whether what is the relative merits and demerits of your typically of your continuous conduction mode and discontinuous conduction. And this is the typically the third version of the bridgeless isolated flyback converter. I mean here of course, we are using again the two devices in back to back, but we have completely eliminated the you can call it the diode rectifier. So, in this case of course, you can call it one MOSFET conduct for positive half cycle, another conduct for negative half cycle, another diode supplement of it, and then of course, we in the secondary side we have a kind of push pull configuration also. So, this is the you can call it, because sometime we are able to get such back to back connected device as a one module, I mean from some manufacturer for many other application also. So, same we can adopt here also, but the diode bridge is completely eliminated in this configuration. So, the losses are accordingly, and in output also you have only one diode coming into the circuit. So, losses can be reduced in drastically, and you can think about here, I mean diode bridge completely almost eliminated here like I mean also. Then typically that is the operation I mean of power factor corrected bridgeless isolated converter during positive half cycle. I mean this is the positive half cycle on positive side circuit is operating. I mean this really diode help, because the MOSFET cannot have it like a reverse voltage blocking capability, and that is the secondary. That is for positive half cycle. Of course, we make I mean like on off and then energy transfer, and for negative half cycle we, because that polarity will be negative. So, it will be conducting virtually in this manner as it is shown by the arrow, dotted arrow, as well as output conduct in the similar manner. So, you can call it I mean the negative of the supply, but you can understand I mean we are able to eliminate completely the diode bridge rectifier from the input in this case also like. So, coming to design approach of this, the average input voltage I mean which we can find out typically I mean the rectified voltage for case of similar to like a diode rectifier, it will be in equal to 2 root 2 Vs upon pi, where Vs is the RMS voltage of the single phase supply, and then relation governing the voltage conversion ratio for buck converter with the turns ratio, we can find out the input voltage and the turns ratio, and then this is the transform of course for buck boost converter, or typically it is a modified version of really simple non isolated buck boost converter. So, this is the same I mean relation d upon 1 minus d, which really explain about the buck or boost operation. So, if d is less than 0.5, then it operates as a buck converter. If it is d above 0.5, then it operates as a boost converter. So, this is the output voltage. I mean of course, this relation is valid for continuous conduction mode like I mean also, and you can call it for continuous conduction mode this inductor, which is like typically your inductance of your magnetizing branch, that I mean you can find out in case of the CCM I mean typically for the flyback transformer from this relation, and if you want to operate in case of discontinuous conduction mode, then this is the typical relation for boundary condition I mean in terms of output voltage turns ratio, then input voltage and equivalent load resistance, then output voltage and duty cycle and switching frequency. So, this should be I mean for critical conduction mode, but for discontinuous conduction mode you have to select certainly lesser than that, but you have to make sure even in continuous conduction mode that at the minimum output power minimum output power and maximum voltage of the input, you should be able to have this typically the continuous current in the inductor. So, that is the condition we have to design for corresponding to the minimum load and maximum input voltage, this inductance we have to calculate corresponding to that. So, V in should be corresponding to the maximum here, and you can call it the corresponding load for minimum power, that here of course, we have to make sure that for maximum output load as well as for minimum input voltage we have to calculate this, because under that condition only this inductance your tendency of the circuit becoming continuous will be there. So, corresponding to that we have to design this like also. So, that is the the interesting observation for the design, because like maybe you might be interested to have a constant output voltage, but the input voltage might vary of the because of the variation in the supply. Like maybe like even in India we have a voltage varying from 170 to 270, or maybe if you want to design it the particular kind of equipment, then like for universal AC mains you want to operate 90 to 270, accordingly you have to design this converter corresponding to whether you want to design in condensed conduction mode or discontinuous mode, and you have to select the right value of these variables like also. And the DC link capacitor, of course, it is corresponding to the here also a single phase converter, virtually single phase AC to DC converter. So, second harmonics will be corresponding in the output DC link voltage. So, and how much is the ripple voltage in terms of voltage, and then ID is the load current of the output, like how much is the load current. So, corresponding to that we have to certainly get the value of this output capacitor. So, output capacitor certainly of course, the frequency of supply is normally constant. So, it will certainly depends, like if you allow more the ripple, then certainly value of capacitor can be less, and if load is more, load means because output voltage is constant like a VD, if your let us say load is more, then the capacitor required more for a particular ripple voltage here. So, it will the value of this capacitor will increase with the load, as well as it will increase with if you want to reduce the ripple across the output across output of this capacitor output of the converter, which is feeding the load like. And then with the typical examples like taking a 200 kilowatt designing at 45 kilohertz, and you can clearly see at supply voltage of 220, which is shown here, that you have a supply voltage, supply current, which is in phase with the supply voltage, and total harmonic distortion is also negligible in this case, and this is the output typically you can think about the DC link voltage, and these are of course the switch voltage, both the switch typically the voltage, and that is the switch current for positive and negative half cycle like also. And the TAD of course, you can see it is quite good, 3.3%. You can see the current is quite good for this PFC, power factor corrected isolated bridgeless flyback converter. This is a harmonic spectrum of the supply current like. Now, coming to the another converter like analysis, design, simulation and performance of power factor corrected isolated bridgeless CUC converter. CUC is the name of the you can call it person who invented this converter, and of course, modification is for the bridgeless with the power factor correction for isolated version of this. So, this is typically isolated PFC converter, you can call it like here. So, we have a MI filter, and we have of course, like here the diode bridge which after rectification, and this is we can call it isolated CUC converter. And we have discussed that this we can design of course, typically maybe because there are 5 energy and storage element, input inductor, output inductor, you can call it your energy transfer capacitor on primary side, energy transfer capacitor on secondary side, and the magnetizing inductance of this transformer like. So, this converter is very interesting in the sense like because of the capacitor presence in input and output, the transformer work ideally even with the operating with the single device. And another we discussed it that you may have to have because there are 5 energy storage devices here. So, you can have a even 2 to power 5 design, means 32 design for this converter. Now, out of 32 design, one of course is the continuous conduction for all this energy storage device like current in the inductors like in Li, LO and LM, and of course, the voltage across C1 and C2. If all these are continuous, then certainly we call it continuous conduction. So, that is a unique design, one design only, and corresponding to that of course, you have to sense the input voltage, input current along with the output voltage which you want to regulate it like but for the discontinuous conduction mode, you might have a like a 31 design, because you might have a all the 5 let us say current in the 3 inductor and voltage across 2 capacitor may be all discontinuous, or it may be discontinuous for 2, 3, 4, or even single one. So, even if it is a single one, you have a 5 design. Like that become 31 design, and you have to select which one is the best and why. So, we look into all the design, and we found that the best design is corresponding to output inductor. And I can tell you why it is so. If you really design the input inductor in discontinuous, size of the EMI filter increases. If you are designing these capacitors into discontinuous voltage mode, then the voltage stress goes multifold across this typically MOSFET as well as diode like. So, because of that, of course, we prefer to have the output inductor to current to be discontinuous, and that give inherent power factor correction, which we already discussed by voltage follower approach like. So, this converter is a quite interesting. In that case, like you have a 32 design, and you can select accordingly one either continuous conduction, but control is reasonably involved with current multiplier approach. You require of course output voltage for control, and you require in that case input voltage, input current for control. But if you are going to be in the discontinuous mode, that output inductor current is discontinuous, then there will be only, let us say you have to sense output voltage for control, and your input, you can call it power factor correction TAD will be certainly reduced, and you will get inherent power factor correction with by design itself like. So, that we call it like a voltage follower approach like. So, controller is also quite simplified in that case like. Well, the bridgeless typically version of it of isolated your Cuck converter, this is first version of the bridgeless you can have. So, you can understand that one operate for positive half cycle and another operates in negative half cycle, but here only the device and diodes are only additional here, but the remaining component either input inductor, output inductor, or these you can call it energy transfer capacitor for between on the primary side and secondary side, and the magnetic transformer or magnetizing this as well as output capacitor and the load capacitor, they are common. So, for making a bridgeless only what we can call it, only you have additional, you can call it like only one diode, one MOSFET, but you are able to get rid of with the diode bridge rectifier, which reduces the losses in this converter. So, that is the typically a bridgeless version of this like. So, bridgeless version means we are able to reduce the losses in the diode bridge rectifier also. And coming to the design of this bridgeless version of it. So, this is the average voltage we are calculating, you can call it the input average voltage to root 2 upon pi into the input supply RMS voltage, and once you know the average input DC voltage, then from this relation you can find out the output voltage, that the relation corresponding to non-isolated topology also for buck boost converter d upon 1 minus d, and then you have a turns ratio of the transformer which can adjust the output voltage accordingly. Even you can design this isolated converter for duty cycle of 0.5. Of course, if it is a non-isolated, there is no concept of designing the converter for 0.5, you have input output voltage same. But here because turns ratio can change your level of the voltage or the output, and many cases we are having multiple output also, like IGBT controllers we are talking. So, you might be having a gate drive for many by IGBT in the circuit. So, maybe one converter can do that job like. So, in that case the turns ratio adjusts the voltage level for the output, because this is also you, but this of course is the fixed one. If there is input voltage variation or load variation, in that case the duty cycle certainly vary over a little around the 0.5 only. The why I am selecting the 0.5, the reason being that your transformer work very ideally, kind of like your duty cycle is 0.5, so it will be almost getting like a quite good ideal supply on input side as well as output side. So, that is the reason we prefer to design it at 0.5 duty cycle, like for this isolated topology like. And then the input inductor current, for the, if you are taking like a typically bridgeless version, so you can calculate from there for a given duty cycle corresponding to that, you can find out from input output and input voltage, then how much current ripple you are permitting and switching frequency there. Normally, in this case the switching frequency in isolated version is further higher than non-isolated version, and the reason being here we are not only reducing the you can call it the size of the inductor of input output, we are able to reduce the size of the transformer. So, you are getting multiple advantage of increasing the switching frequency in this isolated converter like. So, in isolated converter we prefer to have switching frequency much higher than typically of non-isolated version like. So, that is virtually from this we are getting, and for boundary condition this your current ripple, input current ripple will be twice of input. Okay. So, we can find out this even boundary condition inductance also, but we can go typically we can think about if you want to really operate all the time in discontinuous conduction mode, then this inductance should be much lower than what we are calculating for critical conduction mode. But of course, sometime we even design for critical conduction mode, because you want to take advantage of both your typically benefit of your continuous conduction as well as discontinuous conduction. And we already discussed what are the advantage of their relative merit and demerits like. Then the output this output inductor, I mean that is virtually, I mean like we can find out from this relation. Here also depends on your current ripple. If you are going to be like a continuous conduction mode, then this ripple is a prescribed limit how much you can permit in this inductor, because this inductor current is average current is the same as the load current. So, from there we can find out the inductor current, and you can depending upon how much ripple you can really accept it, you can decide that. But when you are going to in DCM for boundary condition, this will be twice of output current, because output average current and inductor average current is the same, because whatever energy going to the typically to the load is flowing through this inductor. That is the reason we call it average current of the inductor, and the load average current is the same. So, it will be twice for boundary condition. Now, we are getting this inductor corresponding to, of course, if you are allowing this ripple corresponding to twice of output or load current, then certainly inductor value will be, this value will be much lower than the what for a particular ripple. But now, if you want to make sure that it is always operating in discontinuous conduction mode, then certainly this inductance value should select much lower than this value also, to make sure that even at the minimum voltage and maximum load you are able to operate, because minimum voltage you will be having maximum current corresponding to the maximum output power. You have to make sure that still it is operate in discontinuous conduction mode, so that you are able to get inherent power factor correction only by typically by design, and you are only using the voltage follower approach by sensing the output voltage only. And these are the of course, the energy transfer capacitor of primary side and secondary side, I mean like typically I mean from these relations. So, that also typically depends how much ripple you can allow across these two capacitors like I mean also. But if you are operating them, designing them again this in discontinuous mode, this voltage also will be can be permitted quite high. But you can understand, because this voltage to be very high, the same voltage gets reflected across the device. So, device rating goes sometime very high if you are designing for discontinuous voltage across these capacitors. So, normally it is not preferred, I mean, but of course, design is feasible, I mean like also, I mean making the voltage across this C1 or C2 or across the both as a discontinuous voltage like I mean. But of course, as I told you, like voltage will increase substantially in the circuit, and that will increase the voltage across the your switching device, so either MOSFET or any other device, as well as it will increase the across the output your diode which is connected in the output circuit like. And then the value of your capacitor, I mean the output capacitor across which the load is connected depends on load current. If your load current is more, this capacitor have to be more for a particular ripple, and also depend on particular how much is the ripple is permitted, and the lowest harmonics certainly in the output will be twice of the your supply frequency. So, certainly this capacitor does not depend, you can call it on switching frequency. However, all other component, if you can look into these inductors, both the inductor as well as both the capacitor, I mean they depends on switching frequency, they are inversely proportional to switching frequency if you look into. So, as you increase the switching frequency, their size will reduce it, but this capacitor depends on the your input supply frequency, I mean in this case I mean or so that is corresponding to reduction of second harmonics like. Now, coming to the case study for 500 watt with the output DC voltage of 300 volt and the supply voltage of 220 and designing at 20 kilowatt, these are the typical waveform, I mean where the output inductors are designed for discontinuous mode. So, this is the you can call it supply voltage, supply current which is in phase, and you can see very clean supply current, and this is a inductor current for positive half cycle, this is for negative half cycle, you can clearly see, and this is the capacitor. So, these are both continuous and capacitor voltage across C1, C2, both are also, these are also continuous voltage, but you can see the output inductor which we design in discontinuous current mode. So, they are discontinuous. So, it means this is virtually the converter which is controlled in the your voltage follower mode with the your discontinuous current mode for the output inductor, these inductor virtually in bridgeless version. And the TAD, this is the supply current waveform, and the TAD of this is from this harmonic spectrum is only typically of 3.56% only. So, which is much lesser than the even a lower value of 5%, which is usually preferred to be like a probably reasonable power level like or so. So, coming to the next another converter like analysis, design, simulation and performance of power factor corrected isolated bridgeless single ended primary inductance converter. Well, this is the typical circuit of this. We have a MI filter, we have a diode rectifier, and we have a input inductor, and the output inductor here of course, we have this inductor as a, you can call it coupling transformer, by which you can adjust the voltage, and you can have a several secondary also into that like also, and this is of course the capacitor for energy transfer. So, here also you can think about like we have a 3 component inductor, capacitor and this inductor, that you can have a 2 to power 3 design. I mean for one for continuous conduction for that all 3, I mean input this current and this current, they are continuous, and this capacitor voltage is also, you can't call it continuous. So, that is one design with the you have to have a current multiplier approach control, where you have to sense output control voltage, you have to control the voltage, but you have to sense input current and input voltage also for making a power factor correction. But if you are designing like anyone, either input inductor or your magnetizing branch of this transformer as a discontinuous current and voltage across any one of the design of 7 design, that you can have a certainly voltage follow approach with power factor correction like also. And this is the bridgeless version of this, I mean like you can think about typically a bridgeless version of this converter, and this is the second bridgeless version of this converter. Typically you can have here the, of course, the you can call it the transformer, of course, we have to put separately 2 transformer, and but the input inductor and capacitors also have to put separately, but input inductor is shared like. But you can consider the diode bridge is completely eliminated here, and you are all the time having only the one device conduct typically coming here in the circuit like also. So, that is second version of it, and coming to bridgeless version, second version, and we are calculating here for the design input average voltage in terms of the RMS supply voltage to √2 upon pi, that is come the average voltage at the normally at the output of diode rectifier, or you can say we are using in this case also even a bridgeless version of this SEPIC converter, and this is the output voltage relation of course in terms of typically buck boost relation and then the transfer ratio. So, that for a given input voltage you can adjust the output voltage a suitable value by adjusting transfer ratio, and certainly you can again design this also around duty cycle of 0.5. Why prefer this? So, that the transformer actions really work very properly in that case like or so, or maybe 0.45 or 0.5 order of that, and this is the input inductor for a given current ripple and switching frequency, I mean like, and duty cycle which we calculate, you can calculate this inductor for continuous conduction mode. But if you want to have a discontinuous conduction, this current ripple should be twice the current, because in input inductor current is the same as the supply or input current. So, it can be like a for discontinuous boundary condition it will be twice of that. So, that inductance value will be much lower than, I mean you can think about here you are going to put like let us say 25% current ripple, here you are putting 200% current ripple. So, in that case will be certainly will be 1/8 will be the value of the inductor if other variables remain the same. So, that will do drastically the size of the inductor, and you have to make sure even while this is for boundary condition, but I mean it should be much lesser than that value for operating this in discontinuous mode in all the operating conditions like or so. Well, the magnetizing inductance you can calculate for CCM in with this relation, I mean that output voltage and the switching frequency and of course, the turns ratio, and then typically here you are taking your ripple current in the magnetizing branch, and this is for CCM for a given ripple current in the your transformer magnetizing current, but you want to have a discontinuous because the you can call it this current will be corresponding for output side, we are calculating in terms for output side, and this will be twice of the your output current load current like So, now you can here again you can think about if it was like a 25% current ripple you are permitting, now you are permitting 200% current ripple in this inductor, I mean magnetizing branch, then the value of the inductor will be much lower for discontinuous, and further you have to take lower than this, so that you are very sure that all the time this converter is operating in discontinuous mode. And of course, this capacitor which typically you can think about of energy transfer capacitor for I mean positive negative half cycle, it also you calculate from this, and it also depends on the voltage ripple how much you are permitting. So, here of course, we do not allow the higher the voltage ripple, because the disadvantage will be that the voltage stress not only across the capacitor, but the switch across the switch as well as across the diode will also increase substantially like. So, you have to increase the voltage rating of those like, and then this is the output capacitor value across which you are connecting the load and the voltage VD there, I mean like there. So, this value also sorry depends on the load current. If load is more, that is load current for a given output power, then your capacitance value will be higher, and if you are allowing the ripple voltage lower the ripple, then certainly this capacitor again will be higher. And of course, I mean it depends on your supply frequency, it does not depend on switching frequency. However, other all you can call it parameters or you can call it component value depends on switching frequency, and that is the reason we prefer to take the switching frequency much higher, because not only we are eliminating these component value, we are able to reduce typically the size of the transformer also, as well as losses in the transformer. So, converter becomes the lighter one, but you can understand the losses in the switching device and diode will increase, provided we are able to have a new devices which can operate high switching frequency. Then only we can get a benefit of reduction of size of these passive element, like in the sense like your inductor, capacitor, as well as of the transformer. Like, well, after the design for corresponding to 800 watt and with the input voltage of 220 volt, 45 kilohertz, these are the typical waveform, like a supply voltage, supply current, and this is the DC link voltage, and this is the, you can call it input inductor current, which are connected on AC side. So, this current and supply current are the same, and you can see the output inductor current, positive half cycle, negative half cycle, you can call it like a, both are here discontinuous. We are designing in discontinuous mode, so that you are able to get inherent power factor correction with the voltage failover control, but the capacitor voltage is made continuous, like and then this is typically you can call it like a, these are the switch voltage for two switches, positive and negative, and the typically the switch currents corresponding to that, and the TAD of this current, you can see this current very clean, and the TAD even less than 2%, like it is order of 1.95%, like for this bridgeless power factor corrected bridgeless isolated single ended primary inductance converter. Like, so, now coming to the another converter, like analysis, design, simulation and performance of power factor corrected isolated bridgeless zeta converter, and this is the typically converter of simple converter of zeta converter, that where we have a MI filter, we have a diode rectifier, and after that we have this isolated zeta converter, where again the number of components are the same as in specific zeta are the same. So, this is output inductor which may design in discontinuous mode, this is energy transfer capacitor, and this is the input inductor becomes like a coupling inductor, or you can call it converted into the transformer. Like, so, here also you can have a design, typically you have a 3 element output inductor, this energy transfer capacitor, as well as the magnetizing inductor. So, you have a 2 to the power 3 design, means 8 design, and you can make a one design corresponding to all our voltage across the capacitor is continuous, and the current in this magnetizing inductance as well as the output inductor are continuous, or you can have a 7 design for discontinuous conduction mode, like either all 3 can be discontinuous, or 2 can be discontinuous, or single can be discontinuous. So, normally we prefer that this output inductor current is discontinuous. Like, so, this is like normal isolated zeta converter, which also can work as a power factor corrected zeta converter, and this is bridgeless version, the first bridgeless version of your isolated zeta converter for power factor correction. And here you can say diode rectifier is completely elemental, this is the EMI filter, and this is typically the kind of the switch. Like, so we are having now, of course, we are able to have still the one transformer, but we have a 2 winding and the 2 switches and 2 diodes we require here, but output side this energy transfer capacitor as well as the output inductor remain the same as well as the output capacitor. Like, provided you have a multiple output, that is the different requirement of application if you need it. Like, so that is the first version, and you have a second version of this typically of your isolated bridgeless isolated zeta converter, where the 2 switches are one conduct for positive and another for negative half cycle, and then you are able to have operation satisfactorily with the this typically of this zeta converter. Then you have a third version of typically of this zeta version, where you have needed 2 transformers separately, which have been earlier converter circuit also we discussed in converter also, but this capacitor and inductor remain the same still. So, it is only the 2 transformer are needed, and this is a EMI filter, such a third version of bridgeless isolated zeta converter. So, coming to the design of this typically, that we have a average input voltage like in terms of the RMS voltage of the single phase supply to root 2 upon pi into Vs, and then the output voltage like V will be D upon 1 minus D, that is the virtually a buck boost operation, that if duty cycle is less than 0.5 we have a buck operation, and if D is above 0.5 then we have a boost operation, and then N2 upon N1 into V in. Normally we can design for given output voltage even duty cycle around 0.5, which we discussed earlier also, and the output voltage can be adjusted by this turns ratio for as far as preset value is concerned. But when the you can call it when load changes, the component drop also changes, or the input supply voltage changes, where this average input supply voltage will change. So, input this average voltage will change or the input, then certainly to regulate the output voltage you have to certainly control the duty cycle, like by of course governed by this relation for typically, like, and this is the relation for your magnetizing branch of the transformer for continuous conduction mode, where you are designing for a particular ripple current and that switching frequency, and duty cycle of course we got from the previous relation. So, this give us the magnetizing inductance of this transformer. And for discontinuous mode, I mean this ripple current, which maybe you might be taking 25% or 10% or so, but now it is going to be 200%. So, certainly size of the inductor will be much lesser than maybe 1/10 or so, but this is corresponding to the boundary condition relation value. But if you really want to operate all the condition in DCM, I mean with this, then you have to take this value further lower than that, like, and to make sure that all operating condition even for maximum output, let us say power, as well as the minimum input voltage, where the current of the input supply will be minimum. I mean like you make sure that it remain even in discontinuous conduction mode, like you select the value of this inductor much lower than that, like also. And then of course, the output inductor for continuous conduction we get from this relation for a given current ripple and switching frequency and output voltage and duty cycle. And this is for of course, output inductor in discontinuous mode. So, here you might be having like a 10 to 20% current ripple, but here you are having 200% current ripple. So, this inductor will be much lower, and it also depends on switching frequency how you are operating. So, and this is only this value is corresponding to boundary condition, but like a critical value LOC, but actual operating to make in discontinuous you have to take further lower this value, like I mean some literature is reported that you can have a 110, but the stress will increase. So, normally half or let us say typically around 75% to half of the value which you calculating for DCM will be quite satisfactory value, like I mean, and this is the energy transfer capacitor value corresponding to, I mean, which you are having virtually in 2 circuit, and that also depends on voltage ripple across this, and this voltage ripple also we do not allow to go more, otherwise the voltage stress across the switch will increase, because that gets reflected across the switch. But all these depends on again the switching frequency, whether you are having this inductor or we are having magnetizing inductance or you are having this energy transfer capacitor, all value depends on switching frequency, and by increasing switch frequency we can get benefit. But of course, the switching frequency is also get somehow counter balance with the help of typically the switching losses in the diode and devices, like, and the output capacitor of course, for across which we are connecting the load. I mean like this is the capacitor which holds typically the voltage, and that depends on the load current for a given particular ripple. It also depends on ripple voltage, I mean how much ripple you can, but certainly depends on it does not depend on switching frequency, depends only your supply frequency. Your second harmonics of supply frequency will be across this, like I mean, so that also I mean like we can design from that, like. So, after typically designing this converter for input voltage of 220 volt and output voltage of 130 volt and the typically 500 watt, and designing for 45 kilowatt with the proper value for in output, again making your magnetizing inductance in discontinuous mode, you can clearly see here. I mean, so this is input voltage, input current, which you can see very close to sinusoidal, and this is the output DC voltage, and this is the magnetizing current of the transformer which made for discontinuous operation, and this is the output typically the inductor current which is continuous, the capacitor voltage is also continuous, and then you can call it like a switch current, typically switch voltage, switch current on both the switches for this bridgeless version of isolated DC-DC converter for power factor. But our theme was for power factor correction, that you can design very well for power factor correction even with the voltage follower approach, even if you make the input current also discontinuous, like I mean also. And this is the TAD of course, here which you can see supply current is close to sinusoidal, and TAD again only 2.81%, like I mean also, and thank you.